First, I hope all of you did get Lab 1 back, so that feedback has been provided. The one thing is indentation, and so I know it may seem petty. However, much of what you have to do as a software engineer is a particular attention to detail. And this is one of the details that matter somewhat. Right? So if you're using Go, you don't have to worry about this. Because if you're using Go, there's a standard formatting, and there's a standard formatter that runs all code through the formatter. And so there's no question about where comments are, whether you use spaces and tabs or anything else. So question number 1 is TY for JOS. What is the standard for tabbing?
I think it's like 6 spaces. I know it's like 1 tab, but like when I...
Okay, it's 1 tab.
Yeah, 1 tab.
It's 1 tab. We don't know anything about the spaces. It's 1 tab. Okay, so they indent via tabs.
No, because when I indent with my tab, because my tab translates to spaces, so it was translating the wrong number, so I figured out I had to like figure out the right number to make it tab correctly.
So the solution there is make sure your editor does tabs. Okay, and for Vim in particular, it's a reasonable question like, how do you use tabs in Vim? And the neat thing is you only have to set 4 different options. So for auto indent, not expand tab, right, because you don't want it to switch tabs into spaces, and where the tab stops are. The default is 8, so actually you could leave that alone. And the shift width, that is, if you do a less than or greater than, it'll shift your selection, and the question is how much to shift. So you can set this in your vimRC, and that'd work okay. Katie, for XV6, what is the indentation? Spaces, how many?
4.
I don't think so. It's 2, so let's see. Yeah, here's sysfile, for instance, and we can see this is 2. So 2, this took me some getting used to. It turns out at Google, their default for C is indenting 2, and so I got used to it over time. But that means actually, unfortunately, you can't share one vimRC between XV6 and JOS. And you're going to be going back and forth multiple times a week between these two. They look very different because the tabs are widely expanded. And just, you got to follow which one it is, because we want the code to look like the rest of the code. Questions on that? All right. Booting. So the question came up last Monday, and I investigated but forgot to mention it on Wednesday. So for booting, on an 8086, right, we have 20 address lines. So basically our address space is from 0 to 2 to the 20th is just 1 megabyte. The ROM, the BIOS, sits at the top of that space. Okay? And in particular, at, let's see what this would be, F0 is where it starts executing. Okay? So, when they went to later processors in the architecture that had larger address space, the question is, where should execution start? And rather than having to start kind of in the middle of the address space, the rule they said was, well, on the 8086, it's at the top of the address space. So let's make it at the top of the address space. There's nothing that requires a BIOS to be there for an x86 processor. Okay? The BIOS is just what makes a PC compatible, right? Going back to the IBM PC, right? But you can not have a BIOS. You can be using an x86 processor for your own use, and it's still going to be starting execution here. But that doesn't mean necessarily there has to be a BIOS here. You got to get something there that responds to the memory access and returns an instruction. Does that make sense? Okay, so if we look at, let's say, the 286, I don't actually remember on the 8286 what its address space is. But let's just make something up. Okay, let's say it's, let's make it an 8386, which I think is 2 to the 32. So 2 to the 32 is how big? Jonathan? 2 to the 32. 1.5 what? All right. 2 to the 20th is 1 megabyte. 2 to the 32, we'd be saying, so every bit we add is doubling, right? And so therefore, if 2 to the 10 is 1,000 and 2 to the 20 is a meg, then 2 to the 30 is? Right, 2 to the 10 is a K, 2 to the 20th is a meg, and 2 to the 30th is a gig. So 2 to the 32 is how many gig? 16. Not quite. So 2 to the 30th is 1 gig, 2 to the 31 is 2 gig, and 2 to the 32 is 4 gig. Okay? All right. And so what happens is execution starts basically over here at FF, 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 F0. All right. So if we take this BIOS for our x86 or 8086 and we try and put it up here and map it, there's a bit of an issue, and that is when we start up in real mode. Real mode says we have no paging, right? And we have these segments that only allow us to address up to 2 to the 20th, right? Because we have 16-bit addresses with a 16-bit segment. And the 16-bit segment can be adjusted right where it is. So if we start executing an instruction here, it's going to be in this real mode. And so how can it execute the next instruction, let's say? Because let's say we do this instruction. Let me see if I give an example. So let's say the instruction is add, 5 to EAX. Except it won't be an E because it's only the 16-bit version. The next instruction is here, right? So this is going to be, well, in fact, this is FFFFFF0. The next instruction will be after that. We better not do an add here. We don't have enough room, right? Because we're about to run out of our ROM. So what had we better do here? We better jump somewhere. Okay, so we'll jump to somewhere. If we jump to that somewhere, that's going to be a 16-bit address. So that's going to be somewhere down in here. But if our ROM is up there, how do we get it to be up there? And so the rule is, after reboot, all instruction addresses get 1s prepended. So in this case, we're going to have 12 1s prepended to any instruction addresses, and therefore things that will be mapped from what would be at 1 megabyte up to 4 gigabytes. And that continues until we get a long jump that switches it into another mode. Yeah.
Why is it a problem if we didn't have the 1s prepended?
Then what we'd have to do is we'd have to have this ROM appear here, and we'd also have to have it appear down here somewhere in the low 1 megabytes, because the real mode, right, so real mode can only address up to 2 to the 20th. And we're in real mode. And so therefore, we can't access any instructions above here. So we'd have to have our ROM appear here and then also here. And prepending the ones is a workaround that fixes that. So I hope that explains was it your question on someone's question about that?
Why not just leave the BIOS in the same place?
So it's common for processors to, when you start up, either start at 0, start at one end of the range or the other, because otherwise what you've got is a bifurcated range where you have some address space here that's RAM and some address space here it's RAM and then a ROM plopped in the middle. And that just is a pain in the ass to work with. So that's why they map it up top. Start up top.
Is there a convention for like non-Intel, like AMD processors? Like, do they?
AMD would be the same because we want to be plug compatible, right? ARM processors are different. I don't know whether they start at 0 or not. I know 68K machines started at 0, yeah.
What plops it at the top? What plops the BIOS at the top?
So there's two things. You've got your processor, right? This is not directly answering your question. It's a precursor to your question. So we've got the processor, and the question is, when you reset the processor, where is it going to go? And that is
Are you talking about BIOS or the
processor, right? The actual expensive chip that I buy, right? So when I turn that on or reset it, where is it going to start executing, right? That is, it's going to send out to the memory bus, right, an address. And what address is that going to be? And it's going to be the top of whatever the address space is for that processor, okay? Then you've got the question as who's going to respond to that? Who's going to respond to FFFFFFFFE? And the question is, we're going to put ROM there that'll respond to that. So we're going to say, you know, if something comes in this high range, go to ROM instead of going to RAM. So there's an agreement, therefore, between the system designer as to where this ROM is, which is really when it retrieves addresses from the address bus, or from the memory bus, which range of that is it going to be sending to the ROM as opposed to RAM, and which processor are you using?
And the BIOS lives in the ROM.
The BIOS lives in the ROM, yes. Okay. But again, there's no requirement to have BIOS to use an x86 processor. If you have a PC compatible, or whatever we call those these days, then it does require some BIOS. All right, so today we're going to talk about overall OS design. So what are the parts of the OS? What do the interfaces look like in particular? How do you use the OS? Why do we have an OS? Why don't we just have a library that we link our application to?
Well, if you want to run multiple applications.
Yeah, if you want to run multiple applications, wanting to run multiple applications is a big reason why we have an operating system. If you have a single application, it can just use the machine as it sees fit. And that may be just a library we link with. So for embedded processors, that's not uncommon to have just a library. Way back when you had, let's say, programs that you'd submit on cards, there was often a library of stuff that you just prepended, some extra cards that would provide kind of the equivalent of an OS. But if you want multiple activities, there are three things you really want. So this is multiple activities, which is really what I'm thinking of as multiple programs. You need multiplexing. You need to share usage of particular things, like memory, like CPU, and so on. You need isolation. That is, you don't want one process screwing up another one. And you want some sort of interaction. You want processes to be able to communicate with each other if they need to. So that's kind of what we're looking at. Often, what's useful is if we provide higher level abstract services. So the raw hardware is not really what programs want to be writing against. They would rather have, let's say, a file system than a raw, a raw disk, let's say. We'd like to have TCP rather than raw Ethernet packets. So we don't actually want to get each Ethernet packet and send back responses and ACKs and NACKs. We want to just get a reliable byte stream, which TCP gives us. Processes are more handy than, let's say, having some sort of raw memory. And they're convenient, and they're portable, and all these things. Perhaps not as performant as let's say the non-abstract. So that's kind of something to keep in mind. We will look as the semester goes on about JOS, about how what JOS exports is much different than what XV6 exports. Okay. And it is more low level, could be more performant for applications. So XV6 has some abstraction. We have processes, right? So processes give us basically an address space and some other stuff. We've got I/O. So rather than having to program, let's say, the Ethernet controller in order to send a packet and the disk controller in order to write onto disk, we have a single call write that works the same way between those two different pieces of hardware. Or to the console. Again, there are a variety of different ways we can write. So read, write, open, close. And then we get the file system, right? So the file system provides us some structure on top of the disk, right? So we've got named files. We've got a hierarchy. We have permissions. Okay, all provided on top. Can you imagine an application or a type of application for which a file system the abstraction is too high?
Perhaps some sorts of databases would want more direct access to the disk so they can optimize performance.
Yeah. Databases a lot of times want to lay stuff out the way they want to lay it out. And in fact, providing a file system makes them have to go to extra work to try and get kind of raw access. So a lot of times what they'll do is just allocate one big file. But that's not necessarily what they really want. What they'd really want is access to the blocks of the disk, or at least part of the blocks of disk. But often for a database, you might allocate an entire disk to it, or more than one disk. And the database would really like to just have that access to that disk. And it'll, of course, run faster. So for processes, multiprocessing. So multiprocessing versus multiprogramming. Multiprocessing really is we're going to use here to say we have a multiprocessor. That is, we have more than one processor, right? Either physically more than one core or hyperthreading where it appears we have more than one core. So in something like that, we've actually got multiple processes running actually simultaneously, right? One CPU is fetching instructions and executing them simultaneously while another CPU is fetching and executing instructions. Okay, now one has to make sure that there are sort of no collisions between those, but that is true multiprocessing. Then we've also got multiprogramming where we have a single CPU and we're sharing that among multiple processes. Okay, so we give the illusion over sort of a long time scale of running multiple at once. But really, we're just time slicing. We get a little slice to the first process, then a little slice to the second, then a little slice to the third, and so on. Okay. Our software, all the software, but not the kernel. So I guess that's not really all, is it? We're organizing as processes. So a process is our program that is our actual code and then the state information running. So what state information do we have for a program? Well, we've got our registers, which include things like our instruction pointer, right, and our stack pointer. The registers, do the registers include the stuff on the stack, Aaron? So, yeah. Yeah, so Aaron.
Oh, you're asking me.
So my question is, do the registers contain the information on the stack? No. Correct, it's just the pointer to the stack, where the stack is. We've also got then that memory associated with our program, which is everything on the stack, all our global variables, or static variables, all of our dynamically allocated memory. Right? Plus, we've got other information, like the file descriptors. What files do we have open? What is our parent process ID? What children process IDs do we have? Okay. So all that state information, along with the code, is the process. Kind of a poor analogy, but is like the program is like a class, and an instance of the class is like a process. So we can create multiple processes from the same program. In fact, it's very common to have multiple instantiations of, let's say, for me, Vim, because I often have multiple Vims sitting in the background or in different windows. And so there, multiple Vim processes from a single Vim executable. Okay, and they've all got different state information. Partially the file they're editing is different, so that file descriptor is different. The contents of the file have been read into memory. That's different in memory. The instruction pointer is different because I'm probably not at exactly the same place, and so on. Make sense? Okay. And then the kernel switches between processes. How? Well, there is cooperative multitasking, where each process basically makes a call and says, I am willing to give up control now. We'll look at that in a moment. There's preemptive, where a timer goes off. Okay. And the we won't say process, the mechanism for switching from one process to another process is called a context switch. So we're switching context from one process to another process, which means all this state information, well, something has to change. Mostly it's the registers. Because if we change the instruction pointer from process A to process B's saved instruction pointer, and we change the stack pointer, then no one's going to reference process A's stack. The stack pointer is going to be pointing at process B's stack. And we need to change the memory map as well. So we'll talk about paging and so on, but we want to protect so that process A only can see process A's memory and process B can only see process B's memory. But mostly, this is just changing registers. Does that make sense? Yeah.
Where are the respective registers stored for each process?
So that's a good question. Where are the registers stored? How does it sound? So let's look at, we're going to have sort of user space here and kernel space here. So this is data that's read-writable by the user, and this is only read-writable by the kernel. What if we stored it, let's say, here in the user space? So this is where we store our saved registers. And then when we come back, we'll restore them from here, right? The kernel will go read them here and restore them. Here's the problem. Well, I'll take it back. That could actually work. The problem I was going to say is if it's writable by the user, then the user process could go change that. But we just said the process isn't running. So if a process isn't running, it can't do anything. It's a deep statement, I know. It's true that a process could go and read this, but in general what we do is we store saved registers in here. Okay, we have what's often called a process control block. process control is really hard to read that way, block. And it's all the information about the process that the kernel's keeping on its behalf. Saved state information, information about the files that are open, and so on. Good question. Drew.
So we use that in kernel space, this combined as illustrating one process.
We'll talk about this in just a second. Just keep in mind that there is space in memory that the user process can read and write, and space that only the kernel can read and write. Okay. So you have this illusion that your process is just running continuously independent of other processes. Right? If you have some sort of communication with another process, that illusion breaks a little bit. Right? Then you have to know there's another process in order to, that may affect communication. And then the other thing that really kind of affects is sort of kind of wall clock time. Wall clock, like the clock up there. Right? Normally, your programs don't use wall clock time. They're using maybe CPU time. How much CPU time I've executed. And you can't really tell the difference whether you're running completely on one processor with no one interfering, or whether you ran for a while and got kicked out, and ran for a while and got kicked out. But if you're actually looking at the wall clock, you may find all of a sudden, you do something, and you look up at the clock, and then you look up 2 instructions later, and the clock is up, changed by 5 minutes. This is a bit of exaggeration, but that can happen. Okay, so the kernel's there to support processes. We have a well-defined entry to the kernel. We'll talk about this in more detail. We've talked about it a little bit already. We have 2 different kinds of entries. So on x86, the same mechanism is used. But we conceptually make them different. So a trap means we enter the kernel because an application specifically asked for it. And that's normally system call. An interrupt is we entered the kernel because of some external event. Okay. And then how does the kernel get control? The hardware, so the processor on a trap or an interrupt, is going to switch from user mode to kernel mode. Sometimes we say supervisor mode, kernel mode, it's the same thing. And then the hardware determines where to go based on a vector at some predefined location. So there's basically some table of if this particular trap happens, this is where to go. If this trap happens, this is where to go, and so on. And then this takes us into some software that actually handles the interrupt or handles the trap. It's got a save state. The hardware probably saves some state. Often this software needs to store more state. We'll talk about this in detail on Wednesday. And then calls some kernel routine. It looks and says, oh, this is trap number 325, which is open. So therefore, let me just go to the call that handles open. And then when it's done, it'll restore state. Unless the reason we got into here was because a timer went off and we wanted to switch to a different process. In which case, don't restore the state that was coming in. We want to just keep that state stored and go restore some other process's state. The user mode, supervisor mode, where that's stored depends on the different CPUs. But somewhere there's kind of this bit that says, what mode are you in? And if you're in user mode, some stuff you can't do. The hardware won't let you. Like changing this mode. Of these considerations we had, isolation, communication, multiplexing, probably the one that has the most, causes the most constraints is this isolation. This is why we end up with these processes with separate address space and separately scheduled CPU. And so the isolation, the basic idea is process A can't screw with process B. Okay? It can't spy on it, can't read data from it, can't modify anything in it, can't wreck it in any way. Okay? So it's memory, it's CPU, it's resources, it's file descriptors, and everything else. I'll give you an example of how you can wreck a fair amount of other processes. And that is start forking, okay? And if you fork, and while you're at it, why don't you have your fork twice and have your two forks fork twice and keep doing that. Fairly quickly, you're going to run out of processes. Okay? And a well-written OS is going to somehow prevent that. Maybe say a particular user isn't allowed to create too many processes. But likely what can happen, and don't try this on Knuth, is you can kill everything, right? So that everyone is stuck. You can't take it, Tim can't go to the shell to fix it because he can't fork from the shell to launch anything, right? So that's an example of a kind of isolation that's often not well dealt with on Linux. So it's a global resource that one user can consume. But it's not really one process that's consuming it. I guess if you look at the parentmost process, in some sense it is, because its tree of children and descendants are actually causing the problem. But you don't want to wreck the OS either. Okay? So there's nothing a user program can do that should cause the kernel to panic. Right? What does panic do? You'll want to use this sometimes in your kernel to deal with situations that are a problem. And it'll just reboot the machine. Okay? So, but the user shouldn't be able to do anything. The user level program shouldn't be able to do anything to cause that. Does that make sense? Does it seem like a reasonable goal here? Okay. So our mechanisms that we're using for this are this user kernel mode, right? Or user supervisor mode, address spaces, time slicing, and our system call interface. These are kind of the things we're going to use to provide the isolation. So the user kernel mode. Can you do these special power things? Right? Do you have access to particular instructions? On x86, it's called the CPL, the current processor level. Yeah.
What do 1 and 2 do?
I'll show you in just a moment. So we're going to have a picture of some rings, and if you have a question still, get back to me. So we have 4 modes, but we care about 2 right now. We have the privileged mode, which is with a CPL of 0, and the unprivileged mode, which is a CPL of 3. So user program should be running in 3. The kernel should be running in 0. And then the kernel is going to get to do extra instructions that the user mode keeps. The CPL protects everything relevant to isolations. So therefore, if we write to the code segment, you can't do that directly, because otherwise we could be changing the CPL. Okay. Every memory read-write is going to be using page tables, we'll talk more about later, which have a different settings for user and kernel mode. Okay? So that allows us to say parts of our address space are not accessible by user if you're in user mode, but are accessible if you're in kernel mode. Accessing I/O ports. So this is one way of doing I/O is using these special I/O port instructions, and so that's limited. And particular registers are limited as well. Question in the back.
So I know that when we were in real mode with CS, that was used for address selection. When you're not in real mode, is it now instead used for CPL, and that's all it's used for? Or?
No. So it's only those bottom 2 bits. The rest of the code segment was used as a base address for your instruction addresses. So it's still used that way.
It's still used for that, even though you have enough bits to access the entire address space yourself?
Yes. So sort of for historical reasons, and no one much uses the segment capabilities anymore. we mostly just use paging. But for backwards compatibility reason, it's still there, and everything still goes through that process. But normally Linux and Windows just kind of set stuff up so that the code segment offset stuff never changes. It's just 0.
What is the HW stand for?
Hardware.
Oh.
From here on out, hardware. And guess what SW is? Very good, Brad. All right. Okay, so we get these rings. I think it was the late 60s that the operating system got created, THE, okay? And it was the first operating system that had this idea of rings. The idea is we have different privileges, and at the there are some things you can only do with the inner privileges. And so we have these inner privileged things, and then at a higher level, we have things that are written on top of the abstractions here. And then outside that, things are written on the abstractions here, and outside that are user programs. So not only just do we have abstractions, we also have enforcement by hardware of ability to do particular things. So that level 0 can say, I have certain stuff that we can only do at level 0. Other stuff I'll allow level 1 and above to do. And then level 1 can say, well, there's stuff only I am allowed to do, but there's other things that I'll allow the higher levels to do. So the x86 supports 4 different levels. So you could have this actually separation of not just user mode, kernel mode, but level 3, 2, 1, and 0, each with increasing capabilities.
What sorts of things can level 2 and 1 do that level 3 can't do?
Well, what happens is when you set up permissions, you basically say, in order to access this, someone at this level or lower. So you could set up a restriction on, I believe you could set up a restriction on a piece of memory that said, if you are in level 0 or 1, this access will work. Otherwise, it won't. Okay? So it's just a slight extension of the binary on or off. And anything that's allowed by when you're in level 2 is also allowed level 1 and level 0. So and the current level, again, is stored in the code segment register. All right, so let's say we want to make a system call. That is, we're running in user mode, and we want to do an open. Okay? How are we going to get from CPL 3 to CPL 0? How does this sound? Pascal? How about we set, so this is our user code, we set the CPL to 0 and then call into the kernel sysopen. Why won't that work?
Maybe we want to, when we turn from the system open, we probably want to set CPL back to 3.
Okay, so one thing is, where's the restore? And I hadn't even thought of that one. To CPL 3. Oh, we'll fix that. Set CPL equals 3. Drew, anything else wrong with this?
I'm not sure if just by setting it to CPL 0, you're actually giving all the privileges required to make the system call, or the other things that
The only knowledge the hardware has about what to allow and what not to allow is the CPL in the code segment. So if the CPL is 0, it'll allow everything. So if we could do this, this would work. The question is, can we do this? What's the CPL right here before we start? It's 3. If the CPL is 3, there's certain things we can't do. What's one of the things we can't do? Set the CPL lower. So if you could, you just, yeah, so CPL prevents this for good reason, right? Because if it, yeah, it's trying to think of an analogy, and I don't have a good one, but you know, you can imagine, I don't have a good analogy. We have this protection, and we say, you're only allowed to do this if you have this particular token, but you can just make up your own token if you want. No, that doesn't help, right? So we can't do this because we can't set the CPL to 3, and even to 0. And we don't want to be able to. So let's look at possibility number 2. We make up an instruction, right? We're designing our architecture here. We make up an instruction, this kernel call. And our kernel call instruction does 2 things. It sets the CPL to 0. So this is 1. And it calls into kernel code 2, right? So this is an address in the kernel. And this is our combo instruction. So Gavin, where are you, Gavin? Gavin, thank you. What's the problem with this?
That's a very complicated instruction.
Is it? It does 2 things.
Fair. What's preventing you from, instead of doing kernel call my own evil function?
Well, my own evil function, well, that's a good question. So what if we have kernel call my evil function, right? Which just does bad things. So where is this located?
Somewhere in memory.
User, kernel?
User memory.
Okay, in user memory. You can understand how to do that, right? So it's going to, my evil function executes the protected instruction halt and catch fire, okay? Which actually there was a documented such instruction for an architecture, and it actually did overheat the system. So, and if you haven't seen the show, it's really good. So that's a potential problem, because that's what my evil function could do. We could modify kernel call and say it'll only go, it won't, it'll look at the address, and it'll say, is this address readable or writable by user? And if so, don't go in there.
Well, then you have the issue that you could jump into some random bit of memory in the kernel, and what if you found some random bit of memory that just happens to contain some evil instruction you want to execute?
Okay, so that's your second problem. So we fix kernel call, so it still goes in the kernel. So this is a kernel, let's just call it unpleasant function. Okay. Looking at some of the attacks that are sometimes made, I think they use what's called gadgets, right? Where they piece together basically small pieces of code that will do certain things and then put them together, you know, to do really bad things. So we can jump into any address in the kernel. I mean, the simplest thing we could do is in the kernel memory, there's data too. So we could jump to an illegal instruction, right? And cause the processor to reset, for example, possibly.
Or if there's any data we can control in the kernel by, I don't know, opening files or whatever, then...
Yeah, so the problem with this is our kernel is wide open to jump anywhere in there. We really don't want the user going anywhere in there. We want them going to some specific place where we can sanitize what happens. And so that's why we're going to have a special instruction that sets the CPL to 0 and calls into the kernel code, but only in the well-defined locations. Okay. So we're going to do an interrupt. Number 64. There are a variety of interrupts. I think the first 32 are defined for hardware interrupts, and the next 32 are software interrupts, like divide by 0. I back up a second, that's not a software interrupt, that's a hardware interrupt. So there's software interrupts, and then there's also, the x86 defines 256 of them. We are going to just use one of them. How are we going to differentiate one syscall from another syscall, Brad? How to differentiate, we're doing an open versus a close versus a read versus a write if we're going to be using the same interrupt here.
It's process ID? Or,
Nope. We're going to use a register. So we're going to use the EAX register. And the EAX register is going to say which system call number is. So we're going to put in a 5 for open, a 10 for close, a 30 for write. We're going to go to this single interrupt, which is going to go to a single place in the kernel. And now we've got what we want, in the sense that we have a way to get from user mode to kernel mode, knowing that when we're done, we're in kernel code, we're in known kernel code that we got to choose as the kernel, and then we can go back with the interrupt return, which is going to restore the CPL, restore registers. This is going to save some registers too.
So just to reiterate, so the application or process that you're running gives EAX the system call number, and then the kernel reads EAX, and then...
The kernel doesn't read EAX. So the kernel doesn't care what's in the registers. The kernel is just going to go to some code. We'll talk about this in more depth on Wednesday. It's going to go to some code that's kernel code, and the kernel code...
But does it do the interrupt 64 based off of what's inside the EAX? No.
So 64 is an operand to the interrupt call. So you could do an interrupt 1 or an interrupt 2 or an interrupt 64. And in fact, an interrupt 1, for example, might be an interrupt, I'm not sure what it is. Let's say an interrupt from a disk controller. You can't do that. You're not allowed to do that from user mode, right? The external hardware can do it. You're not allowed to. 64, we're going to have to set up to say user mode code is allowed to generate an interrupt 64. Drew.
So, wait, so if the kernel does not read the value of EAX, how does it know which system call to go?
The hardware has no idea what system call it is because the hardware doesn't know about system calls. System calls are a fiction of the kernel. The hardware is going to get us to the kernel. The kernel code is going to execute. It's going to look at EAX. It'll have a switch statement that says switch on EAX. If it's 0, do open. If it's 5, do close.
So the kernel code will look at the EAX.
The kernel code will. The hardware doesn't need to.
And this has to do with the hardware.
This is the hardware mechanism we're talking about here.
Okay.
Yep. All right. So now all of a sudden, here's what we've got. If our CPL is 3, we know we're executing user instructions in user mode. And if CPL is 0, we know we're in the kernel, because woe to us if we were actually in user instructions. So we're executing kernel instructions. And we know we got there through a well-defined choke point that we could control. Okay? So what if someone puts in an EAX of 10 million and calls interrupt 64? Could a user code do that? Yeah. Will the hardware care? We'll go into our system call handler, and in our switch statement, we better be able to deal with 10,000,005 or whatever that number was I said. And we better not blow up. We better, what are we going to do? Return an error sounds good. -1, maybe. Yeah. But don't blow up. Do you have to have user kernel mode for process isolation? No. Some examples would be Erlang. So Erlang supports very lightweight processes. But they don't use the kernel processes. It just creates them in user land creates a bunch of these things, and then switches between them, all using user code. How does it prevent one process from messing with another one, reading or writing? The language prevents it. Okay? They have a Erlang virtual machine, and they don't have any mechanisms for reading and writing, and they don't have raw pointers. So language facilities can help. The Singularity OS, let me remind myself on this one. This one does some basically code analysis on processes to verify that they're not going to try and read or write from outside. Yeah.
How is that possible given the halting problem?
They're really good at Microsoft. Now, so what that means is there might be certain classes of programs that aren't allowed, right? Which would not write outside. So I can definitely say here's a class of programs that don't.
Okay.
And there's a whole bunch that I just don't have to decide on. And I'm just say I won't allow those. User kernel modes are the most is what we see most of the time now. We want to isolate process memory. So we want each process to have its own address space. So I'm going to have a process, and it's going to have an address space where, let's say, this isn't necessarily the XV6 process space, but let's just say maybe our code is here, right? So that's all the code that I loaded from disk. We have a stack that's going up from here. We have, let's say, global variables. And we have what's commonly called a heap, which goes down. That's all our dynamic allocated memory, or anything we allocate with new or malloc. And we don't want to, we're going to restrict access to kernel. We're going to restrict access to other processes. So as far as your process is concerned, this is all you get to see. It's all your stuff. You're allowed to, if you want to scribble on top of your code and put garbage here, are you allowed to? Sure. Is it a good idea? Probably not, but you're allowed to, right? Because all it's going to mess up is you, and you're allowed to mess up yourself. So how do we create these address spaces that are isolated? We, on XV6, use, and in JOS, use the paging hardware. So the paging hardware has a MMU, that is a memory management unit. And it does translations from virtual addresses to physical addresses. That is, physical addresses are things that end up on the memory bus. Virtual addresses are the things you see inside the processor. So, right, we've got CPU, we've got memory bus, and between these, we have an MMU. Really, it's part of the CPU, but they used to be, they were actually separate. So the CPU is, let's say, sending addresses to the MMU, and the MMU converts them and then sends them to the memory bus. Get them.
Would it be possible to use the segmentation hardware instead to provide isolation and just set up an identity map in the MMU?
So segmentation used to be done. It used to be used for that, and you can use segmentation hardware to try and do it. But paging is better.
Okay.
So, the 8286 had segmentation hardware, but not paging hardware. The 8386 is when they added that. And I don't know if you remember our little email from Linus about Linux. It was, this is written for the 386 only. It'll never run any other processor. Did you have a question, Kate?
Is IO MMU just like MMU but between the CPU and the IO bus? Or?
IO MMU. Tell me more about that.
I worked at Microsoft.
Oh, and they have IO. Okay, and so.
I heard it was like the same thing, but I'm wondering because of the name change, it goes between.
I don't know, to tell you the truth.
It's
I will try and look it up.
addresses on the PCI bus.
Yeah.
Sorry, what's the difference between segmentation and paging?
We will talk about this in much more detail later. Segmentation basically says, so for a segment, I have a base and a limit. So the base is, if I have, I'm going to say this for right now. Paging is more fine-grained. Okay? Paging, we just operate on chunks of, equal-sized chunks of memory. Segments are different sized and larger granularity. Okay, but we will get to that, yeah.
Somewhat unrelated, but why do we segregate the global variables out from dynamically allocated variables? Why can't we just stick in the same space?
We could possibly, but the global variables, we know how big they are ahead of time. So therefore, it's much easier to reserve. In fact, in our ELF, we have a separate segment for the global variables. So it's just simpler and easier, and they can be distinguished. So I guess another way you could do it is you could dynamically allocate enough space for all the globals and then shove them in there and use the same mechanism. Was there another question?
Yeah, I want to ask about the segmentation hardware, or like translator and the MMU. Does the segmentation happen first and then it gets translated?
Basically, yes. There's actually the CPU. First we do segmenting, and then we do paging, and then we go on. So we can think of them all as just ways of taking a logical or virtual address and converting it to a physical address. The x86 has a more complicated conversion than some other architectures. So ARM, I don't believe, has segmentation, although it will still have paging. So every time we fetch an instruction, read data, write data, anything, in any mode, this MMU, this conversion from virtual to physical is happening, except in real mode. So in real mode, which is what the system starts up in, then you're actually accessing physical memory. Although there's still some segmentation happening, right, as we saw. So normally you get out of real mode pretty quickly. Right? We saw in our boot process how we did that. And once you're in real mode, there's no way, kind of cross my fingers there, it's not quite true, there's no way to get back to real mode. So once you're out of real mode, you're in this protected mode, and it's virtual addresses from here on out. Now it turned out that the BIOS is written in real mode. And for Windows, they often wanted to jump back and to call the BIOS. And they wanted to go back to real mode, but there's no way to get to real mode. So here's what they did. Well, there's one way to get to real mode. When you start up your CPU. So they said, I guess what we need to do is provide a way to start up the CPU, to reset it. So they added some hardware that would reset the CPU and provided a way to control that from software. So that to get back to real mode, you would go to the keyboard controller, because where else would you put this? And to the keyboard controller, write, using the I/O port, to a particular port, a particular location that said reset the CPU. Okay. And then that would cause a reset, and it would come up. Oh, and they'd have to also throw something in memory that says, this is not a real reset. This is just a reset to get into real mode. So it would look at a particular location in memory after it had booted and say, oh, we're just trying to go into real mode temporarily, do my stuff, go back. So, and then it turns out you could do this all in software. From the CPU, you don't actually need external control to the reset if you do a triple fault. So at one time, I think the Intel engineers talked to the Windows folks and said, what would you like us to speed up for future architectures? And they said, we want to speed up handling triple faults. So a triple fault is you're trying to access a virtual address and it faults. That is, there's no corresponding physical address. Commonly, the kernel wants to do something in that case. And then it tries to restart that address after the kernel gets a chance to try and do something. If it causes another fault, that's a double fault. And you only get 3 strikes. And if you do it again, it resets the computer. So that was the new and improved way to get back into real mode. So let's just, for our point, say, once you're done with an initial part of the boot process, it's virtual addresses from here on out. So the virtual address space, we have a space from 0 to 32 meg, 0 to 4 gig. And we break it up into, this is the hardware that's breaking it up, 4K chunks. So 0 to 4K, 4K to 8K, 8K to 12K, 12K to 16K, all of them, these are called pages, have an entry. And that entry says, where should this address go to in physical memory? Where should these 4K values go to in physical memory? And it can go anywhere in physical memory. And then there's another entry that says, where should this 4K go? And where should this 4K go? And where should this 4K go? For all the 4Ks. And a little more information, like what protection do we want to have for this? Should the user be able to read it or write it? Should the user be able to read it? Separately, should the user be able to write it? Or the kernel be able to write it? And so this mapping tells us how to go from this virtual address space into real memory. Kevin.
So if we have 2 to the 32 addresses per process, and we have to store something for every 4K in the address space, isn't that a lot of space taken up just by these maps?
Well, let's see. How much would this be? 4 gig divided by 4K is, so that's 2 to the 32 divided by 2, that's 2 to the 20th, right? So that is a heck of a lot of space. So there are a variety of ways to deal with that. On the x86, you could do one of two things. You can use, first off, it's a 2-level page table. So it's actually broken down into larger groups that then you might not have anything there at all, and so it doesn't cost you. And then you go to the next level. We'll see this all later. The other way you can do it is you can have variable size pages. So you can say, well, this range, 4K is not enough. Let's make these 4 megabyte ranges. Okay, it's a larger granularity. But for now, just look at the page table as this mapping. So the page table specifies how to go from virtual address to physical address. And that mapping is going to be different from process to process to process. True.
This page table for each process.
For each process.
Where is it stored?
Well, it's stored in kernel memory. So inside the kernel, it stores a page table for each process.
So is that in the kernel space for the process?
Yes. So in that process control block I talked about, where we stored a bunch of registers, one of the registers is this page table, and we've got the page table associated with it too. Okay. So the operating system says, as we switch processes, hey, switch this page table. You've got this page table right now. Basically, there's another page table over here. Use that instead. Okay. And that can be quick because it just has to change a register to point from one to the other. All right, so now we've got this, and let me just show you a picture here. So we've got physical memory. And we've got process A, virtual address space, and process B, virtual address space. Okay, process A accesses something the first 4K, right? It's 0000002. Its page table converts that, let's say, to go up to, I don't know, here in memory. Okay? Which is not starting at 00000. Process B has a different page table. And it maps 0 to, let's say, here. Okay? And similarly, all these map to different places. Some of this might map to nowhere, let's say you've got, remember I talked about the fact that we have the stack. You've got space for the stack. But if you haven't used much stack space yet, it need not have actually allocated any space for the rest of it. So it just might say there's nothing there at this address if you tried to go in the stack. Yeah.
And is there cross communication between the page tables so they don't map to the same place?
There is not cross communication between the page tables, but the kernel, as it is allocating physical memory, had better make sure that we don't reuse the same one twice. One way to share information between processes is to map the same memory, that's called shared memory, between two different processes, and this is the mechanism by which that's done. But the kernel's in charge of allowing that, deciding when to do that. Does it kind of make sense? So we will spend much more detail with this. So each page table entry has a bit saying whether user mode can access or not. So here, the bit's going to say yes. The user mode can access it. And yes, and yes, and yes, and yes, and yes. But there's a part of the address space that's reserved for the kernel that it's going to say no, 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 no. So there's a part of address space that the process just won't be able to get to because the process is running in user mode. I mentioned the paging hardware shares memory. Copy on write fork. Remember we talked about the fork? And it has to copy the entire process's address space. We can do some trickery with page tables to delay doing that unless we need to. Same idea with Singularity OS or Java VM. You don't have to have paging hardware to isolate memory if you have some other mechanism, but commonly it's language-based. Right? So if your language doesn't allow you any way and you have a virtual machine that is, let's say, executing these bytecode instructions, you can ensure that there's no messing with. Okay, so that's how the memory isolation is done, with these separate address spaces such that I don't have any way of generating an address that's going to get into someone else's physical memory. In cooperative multiprogramming, multiprocessing, you have process A and it calls yield. And then whatever the next process that's waiting to run calls is executed. This is not that, it's more uncommon these days, but certainly it was common in sort of the original computers, and then as personal computers came around, it was common again then. So Windows 3.1 all use cooperative multitasking there. Mac OS, before Mac OS 10, used cooperative multitasking. So, yield does a context switch. That is, it switches the registers, and it switches, if we have a memory map, the memory map. Okay. And then the yield starts executing in process B, where B last left off. So let's say we look at B. B was running, right? And then it called yield. Now, A actually runs, right? Until what? A calls yield. And now, let's say all we have is these two processors. B starts running again. Where does it run from? From the yield. Like the last thing it did was call yield. So it returns back. As far as it's concerned, it called yield, and it was really slow, and then it returned, right? So it calls yield. It's really slow because something else is happening. And then yield returns and it goes on its way. Bad things about this. Good things, bad things. Giselle.
It kind of assumes, like, it assumes, I guess, some sort of benevolence on the part of your program. So if you have one that's particularly
benevolent user programs. Yes. So that's one thing. If you have a nasty program, what does it do? How can a program be nasty? Yeah, never calls yield. All right? And you saw that on Mac and Windows. Right? Programs, the system would kind of lock up while a program is doing its thing. Advantages are let's say I've got a first-person shooter, and I don't really want my background rendering affecting my first-person shooter. If my first-person shooter just keeps running and never calls yield, my background processing can't take any of my CPU time away. So kind of handy, but in general, every program has to be working correctly. Because if you have any program that isn't calling yield. And the other thing you might find is if you've got a complicated or long-running procedure, you may have to sprinkle yields into it. Okay? All right. Preemptive says forget this trying to ask the application to do it. We will just rip the processor from the process if it hasn't given up in time. We don't need any special code in the application. The processor may be taken from you between any two instructions. So the good news doesn't require cooperation, doesn't require special code. One disadvantage is the OS might not have as much information in the application. The application might know good times to yield, and the application might find it problematic to have to losing control between any two instructions. So, question?
What if you have like a lock around the statement? Can it like context switch between that?
So let's say we had a rule that said if we have a lock, you're not going to get context switched out. Then I'm a bad program. Oh, I want to keep the CPU. I'll get a lock. So no, we can't do that. Even if you have a lock for some critical section, we're still going to kick you out. And we have to ensure that our synchronization works in the face of that.
Can you explain why the OS might not have as much information?
So if I have an application, or let's say I have a set of cooperating applications, I might just know that, I'm trying to think of an example. These other processes are waiting for process A to finish this task. Until it gets that task done, they can't even do anything. And so you're going to have all this context switching back and forth where processes C and D and E may say, oh, look, oh, I can't do anything in return. And process A then is slowed down in getting its job done before these other processes can do it. That's one particular example. Whereas what could happen then is process A just barrels through doing its thing, never calling yield, until it gets to the point that it knows that it'll be useful for other processes to run.
Under preemptive, is like a process guaranteed at a set of instruction. If it wants to like guarantee a set of instructions, be ran sequentially before it gives up processing.
A process cannot, in general, say, I have a set of instructions I need to run. Don't interrupt me in the middle. So, yeah. So how does this work? The kernel can't just give up and start running the user code. Because if it starts running the user code, it may never get back to the kernel. Right? We know you'll get back to the kernel in another system call, right? Or an interrupt. But other than that, you're not getting into the kernel. Those are the only two ways we talked about to get into the kernel, an interrupt or a system call. So we can't guarantee that there's going to be an interrupt, and we can't guarantee necessarily that there's going to be a system call. Well, except there is one interrupt we can guarantee, and that is some sort of a timer. Right? So we have to have a timer for preemption to work. So we start a hardware timer. Right? We either always have a timer running, or we start one running before the context switch. Depends on the hardware. And then we start the process running. If the process makes a blocking call, or in general, calls a system call, then we get back into the kernel, and we can decide what to do. Or if it actually calls yield or some equivalent to say, I don't need the CPU anymore, again, the kernel gets control. Or if the process is destroyed, it would be pretty important that the kernel gets control back. So if any of these three things happen, we're back in the kernel, and it can do its thing. But if that doesn't happen, the user code is just running along, then the timer happens. The timer happens, the hardware takes us to an interrupt handler. The interrupt handler will save the state, go into the kernel mode, and now we can go ahead and figure out the next process. So we save process A's state, but we restore process B's state. And eventually, we'll restore process A's state on some future context switch. Does it make sense? Okay. All right. We will continue on with the remainder of this, and I wanted to look a little bit at shell.c, the homework, as well. So we'll do that on Wednesday. I do have office hours this afternoon. I'll be down in B105. Is that what it is? B105. You guys don't have a homework due on Wednesday, I believe, right? There's one due next Monday. And the lab 2 is due a week from Thursday. But I'd recommend getting started on it, okay?